Session 4.2 Addition Rule and Multiplication Rule. Definition: a compound event is an event that is formed by combining two or more events. Remember the session 4.1, we talked about the simple event. Simple events is only consist one outcome. Session 4.2, we have the compound event. It can be combined like two or more events. Look at this example. Go to a dinner and a movie, and go to the dinner or a movie. I refer to as a compound events. You could say go to the dinner and a movie. This is the two events. Or you could say go to the dinner or a movie. So you only can pick one event. So we call this is the compound events. Look at this notation. Probability of A or B. This is consists like two events in here. Only events A occurs, or only B event occurs, or both events gonna be occur. First, we need to know what's a mutually exclusive events. Two events are said to be mutually exclusive if it is impossible for both events to occur. Mutually exclusive, we also call this as a disjoint. For example, when a corn is tossed, it is impossible to get both a head and a tail. So think about it. When you toss a corn, you only can get head or tail, right? You never get head and a tail at the same time. So we could say head and tails, these two events are mutually exclusive. I can use the diagram to explain this one. For example, the first circle here, this is talking about the probability to get the head. And another one, this is the probability to get the tail. You could see there's a no intersection. That's a disjoint, right? So we're gonna know these two events are mutually exclusive. They can't happen at the same time. When we are looking for the probability or, probability of head or tail, we want to use the addition rule for the mutually exclusive. This is the formula. You guys see this notation? This is means or. Or means probability A or B will be equal to probability of A plus probability of B. One more time. If you are working on the probability or, first, you need to know if this is a mutually exclusive event. Mutually exclusive events means they can't happen at the same time. That's a disjoint in here. If you know this is a mutually exclusive event, you're gonna apply this formula. Another one. We call not mutually exclusive. Not mutually exclusive means both events can occur at the same time. For example, it is possible that I'm eating my breakfast while I'm reading a book. So let me use this picture to explain this guy. Probability of A, let's say a let probability of A will be my eating my breakfast. And probability of B will be reading a book. So this is the probability of reading a book in here. You could see we do have intersections in here. This part means this is the probability of eating my breakfast while I'm reading a book. Both events happen at the same time. One more time. This is a probability of eating my breakfast. This is a probability of reading a book. And the intersections here means these two events happen together. Eating my breakfast while I'm reading a book. And we call this is not mutually exclusive events. So, addition rule for not mutually exclusive. If you want to find probability A or B, just like this one, probability A or B. And if you know this is not mutually exclusive event, so you're gonna apply this formula. Probability of eating my breakfast plus probability of reading a book. So think about it. If I'm adding this probability with reading a book, I duplicate the intersections in here, right? I copied this part like 2 times. So that's why you're gonna take out one of them. You're gonna subtract probability A and B, okay? Remember this notation. Means and, A and B. So keep in mind, if you are working on the probability or first, think about it. Is it mutually exclusive events or not mutually exclusive? And then you're going to apply the formula. Okay, example. Determine the events are mutually exclusive or not mutually exclusive. I want you guys try to do it by yourself. Just write it down, think about it. These two events are mutually exclusive or not mutually exclusive. First one, turning left and turning right. Can you turning left and turning right at the same time? No, right? So this is a mutually exclusive. B, turning left and scratching your head. So can you do it at the same time? Yes, right? So this is not mutually exclusive. C, selecting a student taking a statistic course and is a female. Not mutually exclusive, right? D, roll a die once to get 1 and 2. If you only roll the die once, can you get 1 and 2 at the same time? No, right? So mutually exclusive. Okay, now you guys know what is the meaning of mutually exclusive or not mutually exclusive. Let's apply to the probability questions. "1,000 adults were asked whether they favor a law that would provide more government support for higher education. 1 to 3 decimal space. So I do have the chart in here. This means favor the law. We do have 372 people who are likely to vote and favor the law, and 151 people who are not likely to vote but favor the law. Okay, so if you want to find the total of the people who favor the law, you want to add up these two numbers. And if you want to find out how many total of the people not likely to vote, you're gonna add up these three numbers. Okay, understand, right? So first, what is probability that a randomly select adult is likely to vote? So before we work on these questions, I'm gonna let A will be likely to vote. Okay, A is gonna be likely to vote. B will be the favor the law. So these questions, what is probability that a randomly select adult is likely to vote? So first, I'm gonna write down my notation. I want to find probability of A. Okay, A means likely to vote. And then we're gonna apply the basic probability from the section 4.1. Okay, likely to vote is talking about like this part in here, these three numbers. Okay, likely to vote over the total outcome. How many people are there? We have 1,000, right? So I'm gonna add up these three numbers. They are likely to vote over the total outcome, which is 1,000 people. So you should get 0.721 here. Okay, B. What is the probability that a randomly select adult favors the law? So favor the law, we let with the B, right? So first, write it down, probability of B, favor the law. So how many people are favor the law? You're gonna end up this column, right? And over the total outcome, which is gonna be 1,000. Okay, C. What is the probability that a randomly select adult is likely to vote and favor the law? Okay, you could see there's an and in here, okay? Likely to vote and favor the law at the same time. So likely to vote is gonna be here. And favor the law. So it's gonna be this number. Only 372 people are likely to vote and favor the law. So write down the notation, probability A and B, okay? This notation means and, A and B equal to 372 divided by 1,000, the total outcome. Okay, I want you guys keep in mind for the midterm and finals, if you have a probability questions, make sure you guys state the notation, what you are looking for. Show me your work, how you get this number, and the final answer. And also keep in mind your final answer here, the probability is always in between 0 and 1, okay? If you more than 1 or less than 0 means you make a mistake. Again, make sure you write down the notation. This is part of your credit for the midterm and the final. If they are looking for A and B, so write it down A and B, okay? And write it down what is your A represented to and what is your B represented to, just like here. Okay, next questions. What is the probability that a randomly select adult is likely to vote or favor the law? I want you guys highlight the or. So we have two events in here and we're working or. Remember I say if you're working on the probability, that's a or. You need to think about it if this event is mutually exclusive or not mutually exclusive. Okay, mutually exclusive is going to be disjoint. Not mutually exclusive, they do have an intersection. So if we have the track in here, I recommend you guys circle it, likely to vote, okay? So I circle it, likely to vote. Or favor the law, okay? Circle the favor the law. Do you guys see the intersection in here? Yes, right? That's an intersection in here. So you know this is a not mutually exclusive event. Okay, they can happen at the same time. So write down the formula. Not mutually exclusive event. And then look for probability of A, the likely to vote. Okay, likely to vote is going to be these three numbers plus probability of favor the law, which is going to be these two numbers. And you can see which number is going to be duplicate. A and B, right? So it's going to be talking about the intersections. It's going to be this guy. So I'm going to subtract this. Okay, one more time. Likely to vote, I'm going to add up these three numbers. Favor the law, I'm going to add up these two numbers. And you could see here, you could look at here. We add 372 like 2 times. So that's why we're going to take out one of them. So this is meaning that take out the intersection one, which is going to be 372. Find it out. You should get 0.872. Okay, next questions. What is probability that a randomly select adult is not likely to vote or is undecided? Okay, first step, we're gonna let C equal to not likely to vote. D is gonna be undecided. Again, we are working on the probability with or. So first, think about it. Is a mutually exclusive event or not mutually exclusive? If you're not sure, circle it. Not likely to vote and undecided, right? Undecided, so it's gonna be here. So you can see that's an intersection here. You know this is not mutually exclusive. So we're gonna apply the formula. Can you guys try to do it by yourself? Okay, this is what you guys get. Not likely to vote, you're gonna add up these three numbers. And undecided, you're gonna add up these two numbers. And the 25 was the duplicate one, so we're gonna take out one of them. Okay, you should get 0.366. Okay, F. What is probability that a randomly select adults is favor the law or is undecided? Again, that's a probability working with or. So think about it, mutually exclusive event or not mutually exclusive. Circle it, favor the law, undecided. Do they have an intersection? No, right? This is a disjoint, right? So disjoint means this is a mutually exclusive event. So I'm gonna apply the formula like this. Then plug in the numbers. Okay, you should get 0.635. Okay, so this is the first example. I show you guys how to deal with the probability with or. Okay, one more time, when you're working on the probability with or, think about it, mutually exclusive event or not mutually exclusive. And then you're gonna apply the formula. One more time on the midterms and final, make sure you guys show me your notation. Okay, you could let any letter for what you're looking for, apply to the formula. I need to see this. So all your word, final answer. Okay. Example 3. I want you guys try to do it by yourself. And I already let A equal to pedestrians was intoxicated. B will be the driver was intoxicated. So find the probability that the pedestrians was intoxicated or the driver was intoxicated. So this is going to be or. Okay, or. Think about it. Is it a mutually exclusive events or not mutually exclusive? First, let's circle the pedestrian was intoxicated. And then the driver was intoxicated. So you could see we do have an intersection. So you know these two events are not mutually exclusive. So let's apply the formula. Okay, now what is the probability of the pedestrian was intoxicated? So you're gonna add up these two numbers over the total, right? The total should be 1066. And then probability of the driver was intoxicated, so you're gonna add these two numbers. So you could see for the intersections, this one is duplicate. That's why we're gonna take out one of them. You should get this number, 0.451. Okay, example 4. Calculate the probability of rolling a 2 or an odd number of a fair single six-sided die here. So we are looking for the probability 2 or odd. So think about it, if these two events are mutually exclusive or not mutually exclusive. This is going to be mutually exclusive, right? Because the number 2 and the odd number 135, they don't have an intersection. Now think about it. What is the probability to getting a 2 when you have a 6-sided dice? It's gonna be 1 over 6, right? How about odd number? We do have a 1, 3, 5, right? So 3 out of 6. So you should get 0.6667. Okay, B. Calculate the probability of rolling a 2 or an even number for a fair single six-sided dice here. So you have a 2 and even number. Even number is talking about 2, 4, 6, right? So you can see the 2 and then the 2 here for the even number. They do have an intersections, and this is gonna be not mutually exclusive. Okay, figure out what is this number. Check your work. You should get 0.5 in here. Okay, next one. Conditional probability. Conditional probability of event B given an event A is denoted by, okay, look at this notation. This is conditional probability. And this probability represents the probability of event B occurring after event A has already occurred. And we call this as probability of B given A. Okay, so this is the conditional probability. And for the first part here, this is talking about the probability of B. Okay, so we are looking for the probability of B. And this line here means given that or under the situation A occurs. Okay, so the conditional probability means like probability of B, this is what we're looking for. Under the situation or given that A occurs already. And keep in mind the order doesn't matter. Okay, the first one, this is what we're looking for. And the second one, this is under the condition or under the situation it occurs already. The general multiplication rule. Look at this formula. Okay, this is looking for probability A and B. And then A and B here, this is means event A occurs in the first trial and event B occurs in the second trial. Okay, so A first and then B. So we're gonna apply the conditional probability. The probability A times the conditional probability of B given that A. Before I talk about this general multiplication rule, I want you guys to look at the example and understand the conditional probability. Among these who apply for a particular job, the probability of being granted an interview is 0.1. Among those interviewed, the probability of being offered a job is 0.25. Find the probability that an applicant has an interview and offer a job. So think about it. If you want to get the job offer, first you need to get the interview. Okay, this is the first step. You have to get the interview first, and then you may have a chance to get the job offer. So you can see it here. Find the probability that an applicant has an interview. This is gonna be the first trial. This event occurs first, and then you're gonna get the job offer. This is gonna be on your second trial. So we'll be using the multiplication rule here. Okay, first you're gonna get the interview and then you're gonna have the job offer. So with the questions here, among these who apply for a particular job, probability of being granted an interview is 0.1. So you know that probability of interview here, that will be 0.1. Among those interviewed, the probability of being offered a job is 0.25. So you can see the second sentence here. This is the conditional probability. You will have the probability to get the job offer, that's 0.25, under the situation that you already has the interview. Okay, so the second sentence here, this is a conditional probability, that will be 0.25. So we're gonna plug in the numbers here. You're gonna get 0.025. Okay, one more time. This is an interview and offer a job. It doesn't mean they're gonna happen together. Okay, it means you're gonna get the interview first trial, and then you're gonna get a job offer for the second trial. How can we apply the multiplication rule? Before we're using the formula, we need to know what is the independent event and the dependent events. So what is the independent? two events are independent. If the occurrence of one does not affect the probability, then the other events occurs. For example, tossing a coin, heads or tail, is not affected by the previous toss. For example, now I'm gonna flip the coin 2 times. The first time I want to get the head, and then I'm gonna flip the coins again. I want to get the tail. So what is the probability that I could get the head first and then the tails? So think about it. What is the probability to get the head for the first child? You have two outcomes, right? Either head or tails, and you only have one head. So it's gonna be 1/2. And then second time, when I flip the coins, I want to get the tail. So what is the probability to get the tails? Again, that will be two outcomes, head or tail, and you only have one tail. So it's going to be times 1/2. This is the independence events example, because for the second time, when you flip the coin, the probability of the tail is going to be 1/2, no matter what you get for the first child. Okay, it doesn't affect by the second one, and we call this as the independence event. So I could write the formula like this: probability head and tails equal to probability of head times probability of tails. The second event doesn't affect by the previous one, and we call this is an independence event. So if you know that A and B, these two events are independent, then you could just apply this formula. Okay, the multiplication rule will become probability A and B equal to probability of A times probability of B. Okay, multiplication rule for the dependence event. Dependent. Two events are dependent if the occurrence of one affects the outcome of the second probability. It's going to be different for the independence event. Means that the second probability will be affected by the previous one, and we call this is the dependence event. For example, I need 2 students to help me with a statistic demonstration for my class of 18 girls and 12 boys. I randomly choose one student who comes to the front of the room. I then choose a second student from those still sit. What is the probability that the first student is a girl and the second student is a boy? So think about it. I'm gonna pick the girl first, and then I'm gonna pick the boy. But when I pick the boy, that will be under the situation that one girl is out. So we call this is gonna be the dependence event, because the second probability when I'm picking a boy is affected by the girl. Now think about it. What is the probability for the first child when you want to get the girl? So we do have 18 girls out of the total number of the students, which is going to be 30. So I have an 18 over 30. And then second one, the probability of boy. And this is under the situation that one girl is picked. So if one girl is picked already, so the total number of the students will become 29, right? Only have a 29 students. And then we want to find out probability of the boy. So it's going to be 12 over 29. And we call this is the dependence events because the second probability is affected by the previous one. So if I want to use the formula, I'll be using the multiplication rule here. Probability of girl first and then the boy equal to probability of girl, just like this number, times, what does this mean? This means I want to find the probability of boy given that one girl is picked. Okay, so this is a conditional probability. So we say if A and B are dependent event, then probability A and B will be equal to probability of A times probability of B given that A. And again, this is the conditional probability. Example 2. A bed contains 3 red marbles and 4 blue marbles. 2 marbles are drawn at random. What is probability that the first marble drawn is red and then the second marble is blue? So we have a 2 parts in here. First one, without replacement. Okay, without replacement means after I pick the first marble is red, I'm gonna fold it away. Now I'm gonna draw the second marble. This means the without replacement. So first thing about it, is it a dependent event or independent event? This is a dependent event because the second marble is blue. This is based on one red marble is picked already. So we're gonna apply the formula. This is a dependent event. First, we're gonna figure out what is the probability of the red marble. So total, we have 7 marbles and we have 3 of them are red. So 3 over 7. And then this is the conditional probability. We are looking for a probability of the blue marble, given that one red marble is picked. So now we only have 6 marbles. 1 marble is out already, so we only have 2 red marble and 4 blue marble. So we have 6 marble and then we have 4 blue marble, so 4 over 6. You should get 0.286. Okay, B, with replacement. With replacement means after I pick the first marble red, I'm gonna put it back. And then I'm gonna draw the second marble. So think about it. Is it a dependent event or independent event? That will be independent, right? Because the second marble doesn't affect by the previous one. So apply the formula. This time we only need to multiply probability of red marble times probability of blue marble. Probability of red marble will be 3 over 7, right? And then we're gonna put it back. So the total number of the marble is gonna be still 7. That will be 4 over 7. And you should get 0.245. Okay, example 3. Playing cards. Calculate the probability of drawing an ace or a heart. Here we are talking about the 52 playing cards. If you don't really remember that, you could review the session 4.1, okay? I should have a slide to show you guys all the playing cards. Okay, this is one of the slides from the session 4.1. And we have 52 playing cards. So if you are not really familiar with it, you could look at this picture. I want you guys try to do it by yourself, A, B, and C. And then we're gonna check the word after. And make sure highlight the keywords like here, or. Remember when you see or, what do you need to think about it? And this is talking about and, okay, with replacement. And second one is gonna be without replacement. So make sure you know which formula you need to apply for it. Okay, A. Calculate the probability of drawing an ace or a heart. So remember or. First, you need to think about it if these two events are mutually exclusive or not mutually exclusive. Can they happen at the same time? Yes, right? We do have the ace of the heart. So this is a not mutually exclusive. So write it down. Probability of ace or heart. Plug into the formula. How many aces do we have? We have 4 out of 52. How many hearts? 13, right? 13 over 52. How many cards are ace and heart? We only have a 1, right? So plug in here. you should get 16 over 52. And 1 to 4 decimal space, 0.3077. Okay, B. Find the probability of drawing a 3 and then a diamond with replacement. With replacement means after I draw a 3, I'm gonna put it back and then I'm gonna pick a diamond. So the second probability, it doesn't affect by the previous one. And we know this is gonna be independence event. Okay, what is the probability to get the 3? That will be 4 out of 52, right? How many diamonds are there? 13, right? So 13 over 52. You should get 0.0192. Okay, C. Find the probability of drawing a spray and a heart without replacement. Without replacement means after I pick the first card, I'm gonna fold it away and then I'm gonna draw a heart. So this is gonna be dependence event. Okay, dependence event. So you can see that's a conditional probability here. Okay. You should get 0.0637. Okay, next example. P. Employment job screening results. So we have the tracking here. We have the positive test result and the negative test results, and we have a subject use drugs. Sometimes we have a true positive or true negative in here. So they say if 3 of the 1,000 test subjects are randomly selected, find the probability that they all had true positive or true negative. Is such an event unlikely? So this is a 2 questions, right? First, we need to find the probability that they all had true positive or true negative. Again, when you see or, you need to think about it. Is this event a mutually exclusive or not mutually exclusive? True positive is going to be here. True negative is going to be here. So you could see they are disjoint. They don't have any intersection. Means like this is going to be mutually exclusive. Okay? Mutually exclusive means you want to just add up these two numbers. 44 plus 860. And then they say, A, with replacement means I'm gonna pick the first subjects and then I'm gonna put it back. I'm gonna pick the second subject and then I'm gonna put it back and then I'm gonna pick the third subject. So with replacement means this is gonna be independence event. So now think about it. What is the first one? It's going to be true positive or true negative. The first one, that will be 44 plus 860. One more time, this is going to be the mutually exclusive formula. Only add up these two numbers. And then after we pick the first person, we're going to put it back and then we're going to pick the second person. Since this is a with replacement, so you're going to get the same number. Okay, how about the third one? After you pick the second one, you put it back. You want to pick the third one, same numbers. Use your calculator and 1 to the 3 decimal space. You should get 0.739. Okay, how about this one? Without replacement means after I pick the first person, I forward away, and then I'm gonna pick the second one, and then I'm gonna forward away, and then I'm gonna pick the third one. So this is gonna be the dependence event, right? So first one, when I add up these two numbers, it's gonna be equal to 904 over 1,000. After I pick the first person, I forward away. So the second one, I'm gonna subtract from 1 here. Subtract from 1, subtract from 1. After I pick the second person, I forward away. I'm gonna pick the third person. Use your calculator. You should get the same answer, 0.739. Okay, let me answer the last questions here first. Is such an event unlikely? Remember what is unlikely events? When the probability very small, less than or equal to 5%, right? So here, this is greater than 5%. So the event is not unlikely. Okay, we finished these questions. But think about it in here. How come I have an independent event on the part A and dependent event for the part B? I do get the same answer. If I look back here, I'm supposed to get the answer 0.7387, and this is a 0.7385. Okay, so they only have a little bit difference between these two. I emphasize this part because that's another definition. Treating dependent events as independent. When the sample size is no more than 5% of the size of the population, treat the selection as being independent, even if they are actually dependent. So this is called the 5% rule. You're gonna use the sample size compared with the population. Like these questions. This is my sample size. I only pick 3 people. Out of my population is 1,000. So you can see the sample size is really small compared to the population. So first, we're gonna check on it. We're gonna use the sample size divided by the population and times 100%. So you're gonna see that's a 0.3%. 0.3% is less than or equal to 5%. We could apply this definition. We're gonna treat the selection as being independent. It means that if I have these questions, I'm gonna see dependent event, right? I'm supposed to do it like this way. Pick up one from here, pick up one from here. But since I know the sample size is really small compared to the population, so forget about this one. You could cross this one out. Even though they say without replacement, I will consider this is gonna be independent event. I could use this solution. Okay? Let's try one more example. Assume that we have a batch of 100,000 heart pacemaker, including 99,950 that are good and 50 that are defective. If 20 are randomly selected without replacement, find the probability that they are all good. So first, we have the sample size 20, and the population is 100,000. So think about it, the sample size is really small compared to the population. So we're gonna see if sample size is gonna be less than 5%. So 20 divided by 100,000 times 100%, which is gonna be 0.02%, and which is less than or equal to 5%. So even though they say without replacement, this is the dependent event, we still treat it as an independent. Okay, means we pretend after we pick one, we're gonna put it back and then pick the second one. And then put it back and then pick the third one until we pick 20 of them. So now let's look at the probability. What is the probability that 20 are all good? So first, think about it. What is the probability when you pick the first one is good? We have the total, we have 100,000 heart pacemaker. And then we have 99,950 are good. Okay, so basic probability. The first one is good. How about the second one? Again, we consider this is an independent event, so you don't have to subtract from 1. Okay, this is going to be the second one. How about the third one? That will be exactly the same thing, right? Until we pick first, second, third, fourth, fifth, sixth, until 20th. Okay? So we pick 20 of them. So I could write it like to the power of 20. Use the calculator. Okay, so when you guys working from the homework or midterm, you may have a questions about like the 5% rule here. You have to remember by yourself. Test the sample size to see if this is gonna be less than or equal to 5%. That's it for the session 4.2.